Good evening. Welcome to Krishna's class. Continue with our exploration of the concept of completeness. In this talk, we look at an important example which we come across in analysis, namely all bounded functions on metric spaces under the suit law. Okay. So, X need not be even a metric space. Okay. So the theorem says the following. The normally linear space Px infinity, which is a metric space, is complete. This is a statement of it. Now, what we mean by Bx is this. X is a non-empty set and Bx is the set of all f from x to, we take real value functions for the time being, but all what we do can be repeated if we take complex value functions on x. A bounded function. That means given f, there is a certain m such that mod fx that's what. Now we define the norm, what is known as the sup norm is defined as supremum of x belonging to x this is the sup norm. What we assert is the following. Set of all bounded functions defined on x, bounded real value functions defined on x, which you know forms a normally linear space with the supremum norm. The sup norm is defined as in this way, and the norm of infinity exists because f is bounded. Okay. So what we assert is that, now of course this is a metric space. X is a metric space. Bx is a metric space. As we know, with B, F, G. If you want, you can write here D. This as the metric. In fact, it has more deeper structure than this. That means it's a normed linear space. Okay. Now we prove this result. What we do is we take a Cauchy sequence and then show that it converges to a continuous, it converges to a real valued bounded function on X. Okay, so proof. Let Fn denote a Cauchy sequence in X. That means what we have is this. Because then the sequence Fn is uniformly Cauchy What do we mean by that? See, what we have is this norm of Fn minus Fm infinity. So, given epsilon positive, there exists n epsilon such that this is less than norm of Fn minus Fm is less than epsilon for every epsilon. But that of course means the following. You have Fnx minus Fm which is less than or equal to norm of Fn minus Fm at infinity. Fm infinity. And you see that Fn is a Cauchy in Vx means that for each x, Fnx minus Fmx is a Cauchy sequence of numbers. Okay, that means what we have is this. Now this is true for every x belonging to x. Therefore, Cauchy on x, which means the following, that this is sequence Fnx, or what you call, so the sequence Fnx for each x is a number sequence, okay? Real number sequence. What we are saying is that it is Cauchy, but Cauchy at the same rate, independent of the particular x, the value x, that is why you call it a uniform. Now we shall prove this theorem. Given that quotient sup norm, the number sequence Fnx for each x is Cauchy. Now it's a Cauchy sequence in R. Therefore, Cauchy, since R is complete, Fnx is a convergence sequence. So Fnx for each x converges to some number, and the limit of Fnx thus define a function real valued on x that is f of x is equal to limit n tending to infinity as for every x belonging to x. That is the definition of the function. So we have identified the limiting function. See, I just give a feel for what is happening. Then here, see, suppose let us consider a specific example. Suppose zero. Now look at now you see the graph of these functions is enclosed in this. So what you have is functions of this kind. All bounded functions, not necessarily continuous, even discontinuous functions. So what happens is that you are taking a particular x here and then draw the ordinate to this point. So that cuts each of these functions. So you get a number sequence defined like this, something like this, and so on. So you see, you get a number sequence determined, which is called the Fnx, and this is a number sequence. And what we are asserting is that since R is complete and Fnx for each x is a Cauchy sequence, it converges to some number, and that number is defined as Fx. So that is the definition of x. So let's an example. So that gives some insight into the way in which it works. The domain need not be an interval. Okay. So what happens? So now f is defined. Now we prove that F bounded. Therefore, if so, if it is done, then F is an element of this class. So that's the whole purpose. So for that, so if Fn is a Cauchy sequence, then it is a bounded sequence. Why? That is, the X's and M positive such that norm of Fn is less than or equal for every F. And further, what you have is this, that is, you have Fn x is bounded by F. Now fix any x belonging to x. Then we have Fn x converges to F of x as n tends to infinity. Now we use the convergence. So what one does is the following: we exploit the convergence to show that this is bounded. How do we do that? So choose epsilon equal to 1. Then there exists an n depending on x such that less than epsilon for every n greater than nx because of the convergence. And we have, and this is, and mod Fnx is less than 1. In fact, this is, we have chosen less than 1 for every next. And what is the implication of that? Therefore, let us take mod Fx can be now written as modulus of this. Okay. Now this can be written as less than or equal to and this is bounded by m. Okay, and this path is less than. Therefore, your f is a bounded function. This is true for every x. Therefore, f is a bounded. Now, our job is to prove that. So the what has happened is that we have now proved the f that we have identified, which is the prospective limit of the sequence fn, is a bounded. Dx. Okay. Now what we want to show is, so we assert now that okay, that means it is uniformly, that is fn converges to f okay. Now since fn is quotient, there exists n there exists an n naught belonging to n such that by 2. Now we claim mod fx minus fnx is less than epsilon for every n greater than or equal to r. This is what we want to prove, and for x belongs to x. This is what we want to prove. Then we will have the convergence in the norm. That's very simple. It's just a matter of splitting up the terms properly, adding and subtracting some terms, and then estimating them. So we have to work on this fx minus fnx. So mod fx is equal to mod fx minus fmx plus fm minus fnx. And that and this is true for every m. It's just adding and subtracting belonging to m. That is true. And this is equal to fx m greater than or equal to n. And that's equal to this writing out elaborate. In fact, you need only write one just single step. Now all that you need is just to split it up. So you see that this is less than or equal to mod fx minus fmx plus mod and each one of this we have shown that is less than epsilon by 2. So we get this one because of the convergence of Fn to F, the other one because Fn is a Cauchy sequence, or rather uniformly. And this is less than epsilon by 2. And this holds for this is true for every m belonging to n, m n. This is true. And what is the consequence? The consequence is that so that completes the proof here. So you see that Bx with norm infinity is a complete space. So this is the meaning of saying that Fn converges uniform. So we have shown that every Cauchy sequence in Px infinity converges to a function in the same space, and therefore the space is complete. Okay. Now we prove another small result which is very useful, and this is a property which we expect, that is, if xd is a complete metric space and E is a closed subspace of that, then E is also a complete metric space. Further, if E is a complete subspace of a complete metric space X, then E is closed. So either way. Complete metric space. Then E is closed if and only if E with the same metric B is a complete. So what it says is that if you take a closed subspace of a complete space, then that is a complete metric space with the inherited metric. Okay. Conversely, if you take any complete subspace of a complete metric space, then that is a closed subspace. So let us prove this. It's easy. It's very easy to prove. So first, let us assume that E is a closed subspace of X. So we are proving this reduction. Assume E is a closed subspace of claim ED. So what do we have to do? We start working with a Cauchy sequence in E. Okay, right? A Cauchy sequence in E is a Cauchy sequence in X, right? And you know that X is complete. Since X is complete, you see that its limit, it has a limit in X. And what we want to assert is that limit is in E itself, so that E is complete. Okay. So let's then limit exists in X. Let X be the X. That is because X is complete. Now, what we assert is that X belongs to, so we claim X belongs to. Now, clearly, okay. X is a limit point of what have we assumed? We have assumed that E is a closed subspace. Since E is closed, it contains all its limit points. Which implies X belongs to. So what have we proved? Thus, we have proved that, shown that every Cauchy sequence Xn belonging to E or contained in E converges that is E is complete. So what we have proved is that every closed subspace of a complete metric space is complete. Now we prove the converse. We prove the converse. The converse is assume in so let X be a then there exists a sequence where Xn where Xn converges to Now this implies, of course, Xn is a Cauchy sequence. Since E is complete, Xn converges to X belonging to, what does it mean? It implies contains all its elements. That is, E is closed. This is a very useful thing. So to prove, to check whether a subspace of a complete space is complete, all that you need to show that it's closed. Therefore, if it is not closed, it's clearly it's not a complete subspace. For example, in R, take the Q. Q is Q is not closed in R, so also Q is not complete in. That's an example. We'll make some remarks. The set of all convergent sequences Xn L into, where Xn is bounded. Then C is a closed subspace L infinity and is therefore I think we'll stop there for tonight. Thank you very much. I think that's short, brisk lecture.